All right, so I want to get our hands more dirty with more computations for like low dimensional systems and get more practice with quantum algorithms. And we're gonna start with a warm up, and we're gonna do exercises, and hopefully the screen works after a while. And I want to talk a bit about entanglement, just from a probabilistic point of view. There's a lot to say about it, but I just want to begin with a remark about what it means in terms of probability. So let's take a look at the quantum gates that we've seen. This is for the 1 qubit, and these are the different quantum gates, and we saw the poly gates, and then the phase, it just changes the phase, and then what we're going to be working with today is the Hadamard gate. And the Hadamard gate, what we have here is that it maps. So in here we're going to have 0. We identify it with the 1, 0 vector, and 1 we identify it with the 0, 1 vector. So in here, if we do h and apply it to 0, you're going to get 1 over square root of 2, 1, 1, which is going to be 1 over square root of 2, a linear combination of 0 and 1. And if you apply h, the Hadamard gate, to 1, 0, and you get 1 over square root of 2, 1 minus 1, which is a linear combination, square root of 2, 0, and 1. But the sign is changed, and you can see this from this element right here. So it moves it. If you apply the Hadamard gate to 0, 1, it gives you a linear combination, an equally weighted linear combination of zeros and ones. The difference is that the difference is in the phase, in the plus or minus 1. So in both cases, 0 and 1 are going to be equally weighted in terms of probability, but the phase is going to be different. And this phase is going to plays an important role in quantum algorithms, and we'll see it play an important role, and not in entanglement, but the Hadamard gate, we will see it appear for entanglements, and then for the Deutsch-Jozsa algorithm, which I'll describe later, it also plays an important role. So, and then the other gates that are important, we're going to do a 2-qubit circuit, is this control NOT gate, which in here, just to be explicit, it sends 0, 0, x to 0, x. It does nothing, and it sends 1x to 1x plus 1 modulo 2. So even more explicitly, 0, 0 gets mapped to 0, 0. 0, 1 gets mapped to 0, 1. 1, 0 gets mapped to 1, 1. And the last one is 1, 1 gets mapped to 1, 0. So depending on the, how much of that are you guys seeing?
It's going.
All right. Let's just, well, in any case, hopefully you get the picture. So this is just going to flip the second qubit, if the first qubit is equal to 1. and you can figure out linear combinations that way. So the first exercise that we're going to have, here's the answer, really small. The first exercise for you to do, I'll give you a few minutes, is to create a quantum circuit that maps 0, 0 to the linear combination of 0, 0 and 1, 1. And of course, normalized to be equal to 1. In all of the lectures, everything should be normalized equal to 1. If I forget, you should point it out. And the hint here is that I'm going to use these two gates. And for you, the exercise is to figure out in what order to put them in. So I'll give you a moment to try to figure out this circuit. If you have any questions, please let me know, raise your hand, speak up. And yeah, if you want me to go back to the action of the gates, I can do that too. But the matrices should tell you how it acts. Yeah.
Can you say one more time what what each vector corresponds to in the matrix?
Yeah. So this state corresponds to 1, 0, and this one corresponds to 0, 1.
No, in the 4x4.
In the 4x4, oh, so it's gonna be 0, 0, 0, 1, 1, 0, and 1, 1. Does that make sense? Okay. All right, take a moment to turn to your neighbor and see where you stand, and see if you're somewhere.
Basically, just so if you just do the same thing, you just give you this in basis where you want 0, 0, 0, 0, 1, 1. That's like to this matrix.
After here we
Because this one
after here we can really separate them out.
you just apply it.
Yeah, I mean, so
The Hadamard would
You have to use the Hadamard first, because if you use my scroll not first, you just go right, it's 0, 0, 0, 0, 0. So that would just be you have to restart it. So I don't think anything changes until you apply the Hadamard. So you apply the Hadamard, you get this.
And then we do the control, and this one, the first thing is 0, so this one.
Well, it doesn't do anything to the null. Because it didn't specify what its actual was on the other.
This one is basically.
I thought it was like,
Explicitly doing the Hadamard, you can just look at this did to 0. Oh, and then I just made the matrix did the same thing.
Yeah, but I thought they were.
All right, let's try to figure it out all together now. So, since the hint is this two gates, then really it's a choice of where to put the H gate. And where did people put the H gate? Anyone want to volunteer?
Before the control.
Here or here?
On the control.
Top.
So the top.
Yeah, okay. So yeah, so this is controlling the plus gate. So does everyone agree? Any other algorithms? Circuits? I mean, I heard in the discussion one valid point that I'm only specifying the action on one basis element, so potentially there could be other ways to do it, but this is gonna do it. And let's check the computation. Right, this should be it. So this is the way that I'm denoting it. This 0, 0 is going to be this tensor product. And in here, the Hadamard is going to be acting on this, the top one, and the identity on this one. And then we're going to act by the control gate. So the way that we read the circuits is from left to right, and then we put the qubits right to left. So whenever we're doing the linear algebra, it changes direction. So be careful. Does that make sense? How if I'm reading the circuit, I'm reading it from left to right, but when I'm inputting the vectors, I put them, the direction goes right to left. So since this is first, then this goes here, and then this goes here, this goes here. So in any case, in here, when I apply the Hadamard gate to this 0, 0 state, the action of the Hadamard gate is just going to give me 1, 1. And then the control gate, it depends on we gave the action on the basis 1, 0 and 0, 1. So I split up this vector really into 1, 0 plus 0, 1. And in this case, nothing happens. So I have that this is equal to this. And then in this case, it flips the bit. So in this case, I flip the bit this way. And then this is now going to be equal to 1 over square root of 2, 0, 0, plus 1 over square root of 2, 1, 1. Does that make sense? And you can do the computation other ways. You can just work with the basis and do the linear expansion, but I did it with the vectors in this case. All right. So this is a quick warm-up. Now I want to go into entanglement. I didn't get to, I don't know if you guys noticed, but I didn't get to add all the colors to my slides today. So bear with me. I know you might be confused with the lack of color. But here, for a composite system, what I call a product state. So if I have a composite system made of these two Hilbert spaces, HA and HB, I call the product state to be a state of the tensor product of the Hilbert system. This is such that this state is the tensor product of two states in the Hilbert spaces A and B. And otherwise, I call psi an entangled state. And what I want to do in the following computations and in the following slides is I want to give interpretation of entanglement in terms of probability. And I'm not going to spoil the ending, and I want us to work through it together and figure it out. So we'll do some computations towards that. A specific example of a product state in this case, where we have that both Hilbert spaces are C2, which have basis zeros and ones, would be that any state in the Hilbert space HA and HB can be a linear combination of the basis vectors. So we would have that the product state is of this form, and in particular, it means that we can write this as once we distribute the tensor product, it's going to be AC0 plus AD0, 1 plus BC1, 0 plus BD1, 1. So in here, being a product state really gives some structure to your coefficients, where they're essentially products of this four numbers A, B, C, and D. And again, of course, I'm assuming that everything is normalized. And we'll see how this structure plays into the probability interpretation. And this exercise now is to show that this state that we just created with the Hadamard gate is an entangled state. Yes,
On
Ben.
the previous slide, that first 0 is a 0, 0, right? In the red down there? The next slide.
AC.
0, 0, yeah. Thank you. And this exercise, we want to show that the state that we created with the Hadamard gate and the control NOT gate is an entangled state. All right, turn to your neighbor and see where you stand right now, and see if. No idea. All right, good to know.
Do you think
We want to show that this isn't the case.
It's the sum of two.
So if it is a process using the thing that we just found,
Because it's a sum
that
of
would mean that
zero.
there's, it says A, B, C, and D, such that AC.
No, because in the previous slides I had the sum of the four things with A, B, C, D, all the things, and then when I
In order to
distribute
have
the
the
tensor product,
either A is 0,
you have
this has to be.
some coefficients.
the opportunity
Yeah,
of
there's no like, there's no way you can make
There's
it
no round
like
off,
something
huh?
can be 0 and something else.
Yeah.
It's not 0, so there's no valid combination.
Okay.
Therefore, we can create a normalized state.
Go back to those angles.
Yeah. So somehow
Oh yeah, AC.
somehow you have to have A, B, C, D's that satisfy this condition that norm are equal to 1 and that when you expand it out they're like this. So for the state that we're looking for, this has to be equal to 1 over square root of 2, this has to be equal to 1 over square root of 2, and this has to be 0 and 0. Does that make sense?
That makes sense.
So, and actually, let me go through it. So, if it's a product state, it implies that, again, it's going to be the tensor product of two states in each of the Hilbert spaces. And then when we expand it out, we obtain these coefficients for the different states. And in particular, we want the coefficient in front of 0, 0 to be 1 over square root of 2, the coefficient in front of 0, 1 to be 0, the coefficient in front of 1, 0 to be 0, and the coefficient in front of 1, 1 to be 1 over square root of 2. And by looking at the first two equations right here, this tells me that A cannot be equal to 0. And since A is not equal to 0, this tells me that D is equal to 0. And now that implies that BD is equal to 0 because D is equal to 0. But here we have that BD is 1 over square root of 2. So in this case, we can't have that this state is a product state. It's going to be an entangled state. And this is where things start becoming different from the classical case. Taking the tensor product of two spaces creates much more information than just having products of, or the Cartesian product of two states, of two state systems, or state spaces. So it creates entangled states which are not part of the classical picture. And so this is where we start seeing the difference in the quantum case. We create more possible states. And the interpretation is that or actually we'll get to this, to the interpretation of entangled states. But the interpretation about this, the states for a quantum system is that if we have this state, it means that the qubits are in a superposition with equal probability of being 0, 0 or 1, 1. So they're both happening at the same time. More exercises. So in here, I'm going to let psi be a product state, and which means that psi is equal to this. Copy. Paste. This is, and let's do. This is psi, and we want to show that the probability of measuring the first qubit to be equal to 1, and the probability times the probability of measuring the second qubit to be equal to 1 is equal to the probability of measuring the first and second qubit equal to 1. So in here, x1 is first qubit, and x2 is second qubit. So take a moment to think about that. Actually, since this might be a little bit more involved, let's focus on computing the probability that x1 is equal to 1. and then we'll compare, and then we'll focus on the probability that x1 and x2 is equal to 1, 1. So first work on this, computing this probability. And these are our coefficients. All right, let's do this first probability together. What's the probability of x1 equals to 1? Sorry, I can't hear you because of the air. Can you repeat it?
The norm of BC squared plus the norm of BD squared.
Everyone agree? So yeah, in this case, it's the first qubit has to be equal to 1, so you have to measure this or this. So similarly, we have the probability of x2 is equal to 1 is equal to what? It's going to be equal to bc squared plus, no, x2, ad plus bd squared. Now, someone else tell me what's the probability that x1 is equal to 1 and x2 is equal to 1. Someone that hasn't participated yet. A new voice. Take a shot in the dark. Yes?
It is BD squared.
Yeah, bd squared. So now the problem is to show that the product of this times this is equal to this. So I'll give you one more moment to think about that. All right, in one or two words, why is this true? Or two? Yes?
Factor those.
Yeah, factoring. And the second word that I would take is normalization. That's the other thing that comes in. So does that make sense to everyone? Do I need to spell it out? Nope. All right. What did I do? In here, I want. So this is something else, but let me just. I'll actually prove it here. So in here, I can factor out b and I have c squared plus d squared, and I can factor out d, and I have a squared plus b squared, and that's the factoring, and then the normalization is that each of these is equal to 1 because the states, it comes from a product state, and A0 B1 is one state, psi A, and the other state DC0 plus D1 is the other state. And each of those are normalized to be equal to 1. So now you see that if you take the product, you're going to get BD squared. And the moral of this story is that, bless you, the moral of the story is that if psi is your product state, and it's a product state, then the probability that qubits are independent of each other. They're not interacting. And this is the identity that defines independence and probability. So this is the first hint that of the interpretation for entanglement. If you have a product state, then the qubits are going to be independent. Now, and this is actually, let's skip that. The claim is that that statement is an if and only if statement. If you have an entanglement and it's entangled state, then the qubits are not independent. So entanglement is, the interpretation probabilistically is that the qubits are not independent. So when you make measurements, there's gonna be some correlation between the different qubits. Does that make sense? So in here, the claim is that if psi, and here I did it for the case that we're working with, but it can generalize to any number of qubits. That if we have psi and the first and the second qubit are independent, that's true if and only if the state is a product state. So here is the proof. My notes are a little rough around the edges today, so bear with me. So I'm going to start with psi being any state in a composite system. And we don't, since we are not sure that it's, what we want to prove is that it's a product state, we have already shown that if it's a product state, then it's independent. And what we want to show now is that if it's independent, then it's a product state. So I'm not going to assume that it's a product state. I'm going to just take any general state, and with parameters, with coefficients alpha, beta, gamma, delta. And I want to show, and I'm going to assume that it's independent, that the qubits are independent. The computation that we did, that x1 is equal to 1, x2 is equal to 2, and they're independent, is the following. It's equivalent to this one, where we have x1 is equal to 1. We just consider the two possible cases where x1 could be equal to 1, this case and this case, and we add the probability of each of those cases. Written explicitly is here. And then the probability that x2 is equal to 1 is this case and this case, so we have this. And then the probability that x2 and x1 are both equal to 1, it's this case. So we get this probability. So this gives us this identity. And if we do the different cases for the other possible states of the first and second qubit, if we do this one, that the first qubit is 1 and the second qubit is 0, we get a similar identity. And if we do the independence for the first qubit being 0 and the second one being 1, we get this identity. And the last case where both are 0, we get this identity. And what we want to do is we want to write this in, I forget, in this format. We want to write it as a product state. So the goal is to find A, B, C, and D so that we have this identity. And in here, if I pick A, B, C, and D by inspection, almost. For instance, in here, and these identities have given me that each of these elements, I can write it as a product of two numbers. So a product of a number and a number, a product of a number and a number, a product of a number and a number, and a product of a number and a number. But I have to figure out what B and D are, and A and B, and C and D. So I want to figure out what all of them are. And what I do is I look at the formula for delta, and it's going to be BD. And I look at the formula for gamma, and it's going to be BC. So they're going to have a factor in common, and that's going to be B. And if I look at the formulas in here, I look for a factor in common. And in this case, this factor and this factor is the same. So that's going to be my B. So this is going to be my B. And then I just continue doing that. If I look at A, C, and AD, they're going to have a factor in common. And this corresponds to this case. And that means that this is my A, the square root of A. And then I have A, B, and then C is going to be the common factor of this two. It's going to be the common factor of this and this. And that means that C is going to be this one. And then D, we can figure it out. And then I normalize, so I'm figuring out what the norm square is equal to. So I take the square root, and then there's the phase factor, but that doesn't affect the probability. So I just take the regular square root. And then I get that I can write this psi in this format. So, close call. So this is what I get. Questions? So, in probabilistic terms, this is what entanglement means. Qubits, bless you, qubits are not independent. So this is the way to think about it. Now we're going to move to another application, another use of the Hadamard gate. I don't think we're going to get through it all, but I'm going to set the stage for this specific, I've forgotten this, a specific quantum algorithm where we'll start seeing the advantage of using quantum computations. So in here, we're going to have a function that's from the set 0, 1, 2, all the way to 2 to the n minus 1. And it's either going to map to 0 or 1. And we're going to consider only two cases. One where f is a constant function. Either it's all equal to 0 or it's all equal to 1. Or it alternates between the 0 or 1, but in not necessarily periodically. Half the numbers take the value 0 and half the numbers take the value 1. And it could be any of those functions. So If it's constant, we say that the function is constant. And if it satisfies this condition, where half the numbers take the value 0 and the other half take the value 1, then we say it's balanced. The problem here is an algorithm to determine if f is constant or balanced. And what you can do is you can evaluate. So the measurements, in the classical sense, the measurements are evaluating the function at different values. This is what you can do to figure it out. Measure or evaluate the function at different inputs. And then based on that, you try to determine whether f is constant or balanced. So for instance, we'll assume that each f is equally likely. It's equally likely between being balanced or constant. And we look at the space of all these f's. And what I'm going to do to try to determine this classically is to start evaluating this function at different values, at different inputs. So if I measure that f of 0 is equal to 0, what information have I gained? It's not constant 1, but it could be constant 0. And it could be balanced. So I've gained no information. So the first measurement gives me nothing. I can't compare against anything else. So 50% of the time it will be constant and 50% it will be balanced. So I haven't gained any information, it's still 50-50. Then my next measurement is evaluating f of 1. And let's assume that f of 0 is equal to f of 1. My claim here is that the probability that it's balanced is going to be equal to this product. Once I made this, once I made this two measurements. And how does this happen? I could, just by random log, since half the values of a balanced equation are going to be the same, if I measure 2 and they're equal to the same in a balanced equation, then the probability is going to be given by this. So I measure the first one, and the probability that the second one's the same in a balanced equation is going to be this. And only in those cases will I get that they're equal to the same in the balanced equation. So this is going to be my probability that it's a balanced equation. And otherwise, it's going to be constant. So if I get 2 consecutive measurements that are equal to each other, it's telling me that it's more likely to be constant, but I haven't figured it out yet. And a small exercise that I was going to have you do is show that what the probability of being balanced is after measuring the first k values, or the first k plus 1. But let's just spoil it. This is going to be 1 times n minus 1 over 2n times n minus 2 over 2n. Oh, and here, I forgot to say 2n is equal to 2n. Or n is equal to 2n minus 1. 2n, and then all the way to n minus k over 2n. So, okay, did it the other way around. The probabilities of being constant. Sorry. No, balance. Yeah. No, that was right. Balanced. So if I keep evaluating the function and I keep getting the same number, the probability that it's balanced starts to decrease. And at what point will the probability be 0 that it's balanced if I keep getting the same value for the function? How many measurements do I have to do? What does k have to be equal to? What's that?
I was gonna say n over 2, but
Close. Any other takers?
n over 2 plus 1.
Not that close. So I have two n values, and half of them, n of them are 0, the other half are 1. How many do I have to measure before I know that it's constant or balanced with 100% confidence? N plus 1, yeah. So in here, n, k has to be equal to n. And you'll see here that in this formula, if k is equal to n, then the probability of being balanced is 0. You're multiplying times 0. Yeah.
Why do we have 2 n values instead of n values?
Set it up at the beginning or something.
I called it little n. So yeah, I think this might have been a little bit confusing. So in here, I did the number of elements, 2 to the n minus 1. So this is, since I start with 0, these are going to be, the total number of elements is going to be 2 to the n. And this is what I call 2 to the n, 2 times n. So I just did it so that I wouldn't have to say n over 2, which that was your answer. But maybe that's where it got mixed up. But to show that, I just want to make sure that n over 2 in my notation, I didn't want to have my notation have n over 2 because I want to make sure that n over 2 is an integer. But in any case, that initially we have 2 to the n inputs, and since half of them are 0 or 1, if we want to know for sure whether it's constant or not, we have to measure more than half of them. Because the worst case scenario is that you get really unlucky and it's going to be really small probability, but you just measure all the ones that are the same in the balance case, and then you have to do one more to be sure. And you can actually think about it probabilistically. How many measurements do you have to do to have a confidence of that with probability less than or greater than epsilon that is balanced or constant. But the idea here is that to actually determine whether it's constant or balanced, you have to do n plus 1 measurements, or half plus 1 of the total number of values. And in the quantum case, what we'll see next lecture is that the claim is you can do it in one measurement and figure out whether it's constant or not. So this is a hint of the possible applications and speed up of quantum computing. Any questions before we wrap up? Yeah.
Never mind. Why didn't you just call when we set up our initial, why didn't you just call that 2n to begin with? What was the point of writing it as 2 to the n minus 1?
Because the numbers, the way that I'm going to represent it with like quantum circuits is going to be with qubits, which could be zeros and ones, and the total number of different qubit expressions are going to be 2 to the n minus 1. So I'm thinking of numbers in terms of base 2. So it's coming up in the way that I represent these numbers as qubits. So that's the 2 to the n. Yeah. All right, that's it. Thanks.